So hello everyone, my name is Mark Rancourt. I'm a wastewater process specialist with Bishop Water. I've been working in the water treatment industry for the last 15 years now, across various sectors such as municipal wastewater treatment, food and beverage, and metal finishing. I'll be co-presenting with my colleague Christine Gann, who will introduce herself shortly.
Thanks, Mark. As he mentioned, my name is Christine Gann. So here at Bishop, I'm a wastewater and engineering specialist. I've been in this role for about 4 years, and I've helped to design and implement projects using a number of our solutions for both solids management and nutrient removal. And this now includes ClariPhos projects for phosphorus removal as well. So I'm very excited to be here with Mark to introduce this advanced coagulant and explain how it works.
All right, thanks, Christine. So let's begin with a brief overview of ClariPhos. So it's an advanced coagulant that allows for rapid and stable precipitation of phosphorus from wastewater. It's made with lanthanum and cerium, two rare earth elements that have a very high affinity for phosphorus and enable ClariPhos to form a dense precipitate that settles up to about 2 times faster than conventional aluminum or iron-based coagulants. So in short, this means that a wastewater plant can achieve ultra-low phosphorus limits using a simple chemical treatment process, and can avoid spending millions in a lot of cases for complex tertiary filtration systems. Most of the treatment plants that are using this technology simply made the switch from alum or ferric coagulants to ClariPhos using existing plant feed equipment. So very simple, affordable option for hitting lower phosphorus limits while also gaining many other economic and operational benefits, as we'll soon discuss. So those aforementioned characteristics of the product represent a significant advancement in chemical treatment. We know that many municipalities and industries are facing lower phosphorus limits and often consider equipment upgrades to improve phosphorus removal, but tertiary filtration systems can be very expensive, and many municipalities that are in that situation are simply not fully prepared to take on the financial burden of upgrading their plant's equipment. And in addition to capital costs, these systems also come with higher operating costs for sludge handling and disposal consumables, such as media replacement, media cleaning chemicals, and also higher energy requirements. Just to give you an example of the potential costs, I can refer to this 2017 energy conservation report put together by the Environmental Commissioner of Ontario. And in this report, it was estimated that the equipment cost of upgrading existing treatment plants in Ontario to meet tough phosphorus limits ranges from $5,000 to $45,000 per kilogram of phosphorus removed. And I'm sure it's safe to say that since 2017, that cost estimate has risen substantially, like everything else these days, unfortunately. And keep in mind that's only taking into account capital costs, so it doesn't even include the higher energy costs associated with running those types of systems. So we're talking about pretty significant expenditures over the long term. So it's pretty clear that if a coagulant alone can enable a treatment plant to achieve its phosphorus limits and avoid the equipment upgrades, then there can be considerable cost savings to be realized. Another area of significant savings with this product is in sludge production and sludge management. Because ClariPhos works so much better than aluminum or iron chemistries, you'll require much less dosing comparatively to get the desired results. We'll get into the chemistry of how and why that works in a moment, but for now, I just want to emphasize it's not uncommon for treatment plants using ClariPhos to reduce chemical sludge by as much as 50%. And not only that, they also experience improvements in the dewaterability of the sludge by as much as 40%. So, think about the savings a plant can achieve if you had half the sludge, and it's also much drier when you need to dispose of it. ClariPhos also offers benefits for plant maintenance and operator safety. One of the biggest benefits in this area is that ClariPhos is about 100 times less acidic than alum or ferric. So pH adjustment is often not even necessary or greatly reduced. It also doesn't stain or discolor plant structures and equipment, and it's also rated non-hazardous. So very very safe for operators to store and handle. So we're often asked about what type of system is best for ClariPhos, and really the simple answer is any type of system. It's true even if phosphorus levels are in pretty good control already, since there's many other benefits to ClariPhos that will help improve overall efficiency of the treatment plant. So really that means it's ideal for just about any treatment plant that's already equipped for chemical phosphorus removal, or if not, it can simply be added to its process. So this includes, systems such as conventional activated sludge plants, industrial clarifier systems, MBRs, RBCs, MBBR, you name it. Really, it can be implemented anywhere. So here's just a quick snapshot of how the benefits of ClariPhos can be realized among a few different types of systems, but by no means is it limited to these systems. So just a quick point of reference here. To start, conventional treatment plants would likely see the biggest benefit with a reduction in sludge volumes, which would also result in improved clarifier performance and dewatering performance. It will provide other benefits, such as preventing struvite and eliminating staining, which is commonly seen when iron-based chemistries are used. Any plants using UV sterilization will certainly know that UV transmittance can be negatively affected when excess chemical is present in the water. So ClariPhos is certainly proven to be a benefit in this regard. MBRs will be able to reduce overall chemical consumption, many times including caustics, since less acidity will be added to the system compared to other coagulants. So just helps simplify overall plant operation, improve operator safety, since they'll be handling less coagulant, less caustic, and also maintain a healthier population of the microbes, and it'll eliminate those swings in pH, which can be problematic. Lagoons rely on settling solids, obviously, to achieve discharge targets. So ClariPhos will improve settling rates and reduce the likelihood of TSS carryover, since it does settle up to twice as fast as conventional coagulants. And although sludge cleanouts aren't done on a frequent basis in lagoons, overall sludge accumulation certainly will be less over time. Industrial clarifiers also rely on settling, can build up lots of sludge if not managed properly. So ClariPhos will help in both those instances. These systems often rely on filter presses or belt presses to dewater sludge, and ClariPhos has been shown to significantly improve dewatering efficiency compared to other chemistries. And finally, as indicated across the bottom in green, it goes without saying for all these systems, the ultimate goal here with this product is to get below those phosphorus limits. So ClariPhos is better suited than any other product on the market to accomplish that. All right, I'll turn things over to Christine, and she'll get more into the details of how ClariPhos works. Over to you, Christine.
Great, thanks, Mark. So okay, let's begin. We can look at the chemical composition of ClariPhos to start, which we have touched on a little bit. It is a chloride-based salt solution of the metals lanthanum and cerium. So these are both found in nature as complexes with phosphorus. Lanthanum and cerium can both form very strong crystalline bonds with phosphate, making them really ideal for wastewater treatment applications where phosphorus is an issue. So quickly, I can review what rare earth elements actually are, just to give you a bit of background and context. So the term rare earth is actually a misnomer because the elements are really not that rare. In fact, lanthanum and cerium are estimated to be the 26th and 28th most abundant elements in the Earth's crust, respectively. So the term rare actually just refers to the fact that it's rare to get a very large concentration of these metals localized into one area, like you might with other metals like gold or nickel. There are 17 rare earth metals in the periodic table, as shown here on the right. They all have similar properties and are often found, like I said, in nature, complex to one another or with other elements. And once a rare earth metal is complex or bound to another element, such as phosphorus, it's very difficult to separate them from one another. So as you can imagine, this is why ClariPhos makes such an effective coagulant for phosphorus removal and why it can offer so many advantages compared to traditional coagulants. So here is the basis of mechanism of action for ClariPhos. Since lanthanum and cerium have a very high affinity for phosphorus, when they come into contact with it in wastewater, a dense and insoluble precipitate forms, which then rapidly settles out of solution. So that precipitate is shown here on the right. It's called rhabdophane, and that is a stable rare earth phosphate mineral, and it's also found in nature. So the advantage of this is that ClariPhos works at binding and reducing phosphorus at only a 1-to-1 molar dosage ratio. So ultimately, you're using less chemical to precipitate out phosphorus, and less sludge is also produced. And once this complex is formed, it will not resolubilize and won't re-release phosphorus back into the waste stream. So that's a pretty distinguishing characteristic compared to other coagulants such as alum or ferric that do tend to re-release phosphorus in downstream processes. So compared to the mechanism of action to alum or ferric, this kind of reinforces why ClariPhos is able to remove phosphorus at such an effective dose rate. Traditionally, it was thought that iron and alum salts always formed a tight bond with phosphorus, resulting in aluminum phosphate or ferric phosphate molecules. But recently, it's been shown that the reaction mechanism is actually a bit more complicated, especially when only low levels of phosphorus are present. So it's actually a two-step reaction that occurs. So first, aluminum or ferric will form these metal oxide intermediates, which is then followed by phosphate adsorption onto the surface of this metal oxide. So this adsorption of phosphorus is a relatively weak surface bond that is reversible and is also non-specific to phosphorus, often resulting in pretty high chemical dosages that are required to achieve low effluent phosphorus concentrations. So if we compare ClariPhos's mechanism of action to alum or ferric, it becomes pretty evident why ClariPhos is able to remove phosphorus at such an effective dosage rate. The benefits of ClariPhos become even more pronounced the more stringent your phosphorus limits are. So this graph here is comparing the molar dose ratios of ClariPhos compared to several other coagulants like ferric and alum to achieve a range of phosphorus limits. So here on the left here is the phosphorus concentration, and on the x-axis here is the molar ratio of the coagulant that's needed. So you can see that as the phosphorus concentration that you're trying to remove drops, you get an increasingly higher dose of chemical that's required for coagulants such as alum or ferric, but not for ClariPhos, which is shown as this blue line here. So you can see that even at a phosphorus concentration as low as 1.1 or 0.05, the molar dose ratio remains quite close to 1-to-1 with the rare earth chemistry, and requires significantly lower dosage compared to ferric or alum. And that's because of that specificity, again, to phosphorus rather than just the hydroxide intermediate that adsorbs phosphorus. So the lower dosage required with ClariPhos is why you're able to see such significant reductions in sludge volume as well. So here you can see a comparison between the precipitates of alum, ferric, and ClariPhos. These sludge samples were produced by removing the same amount of phosphorus. So in this scenario, the molar ratio dosage for ClariPhos remained at 1-to-1, whereas for alum, it was 4-to-1. And in addition to the higher chemical dose, alum and ferric both also produce larger quantities of intermediates that contribute to sludge formation. And as a result, the rare earth coagulant can produce up to 51% less sludge than ferric coagulant and about 34% less sludge than alum. So this also means that you can achieve some pretty significant cost savings. One report that was produced in Vermont estimated that approximately 40% of a wastewater treatment plant's total annual operating budget is spent on sludge management. So you can imagine how this reduction in sludge can be very beneficial economically. And in that same report, it was predicted that wastewater treatment facilities should expect to see significant future increases in sludge production because of the increased requirement for greater nitrogen and phosphorus reduction. So it does go to say that this increase would be especially impacted by phosphorus contribution. ClariPhos also enables the rapid settling of the rhabdophane precipitate, even if the particles are quite fine. So this slide shows a pretty nice comparison of settling times between ferric chloride and ClariPhos. As you can see here, 15 minutes post-dosage, ClariPhos settles much faster than the ferric chloride. And that's because the atomic weights of lanthanum and cerium are much higher than those of aluminum ferric. So the precipitate that it forms is much denser, it's heavier, and it's able to be settled out a lot faster. So any treatment plant that experiences sludge capacity issues or solids clarifier or solids carryover in their clarifiers will certainly benefit. Again, the benefit of more efficient settling will obviously help to improve the performance of clarifiers. This is a photo here on the right, which shows some of the problems that this plant was experiencing with a conventional coagulant. You can see that the clarifier was not working very well. There was a significant amount of material floating, whereas the lower photo shows the same clarifier just 48 hours after dosing with ClariPhos. The results are pretty dramatic. You can see that the denser and heavier flock has settled, enabling the clarifier to operate more efficiently. Again, solids carryover was reduced, and they no longer really needed to think about installation of a tertiary filtration system to get rid of those fine particulates. I did mention about the non-resolubilization of the rhabdophane precipitate. So this also means that it won't be released into a digester, and that helps to prevent the formation of nuisance struvite, which occurs when conventional coagulants release soluble orthophosphate during digestion. And that also binds to other molecules like magnesium and ammonia. So as a result, plant efficiencies can be increased, operations improved, and maintenance costs reduced. You can see here from this photo on the right, the difference in struvite buildup from a plant before and after implementing ClariPhos. The top photo shows what a pump looks like after only 18 days of use without the benefit of ClariPhos. So the struvite buildup results in a pretty fair bit of maintenance involved to clean the pump and restore it to optimum condition. Whereas the pump in the bottom photo has been operating for about a year with ClariPhos and has still shown virtually no accumulation, which is another big benefit. So the sludge produced also improves sludge dewatering, which helps to minimize operating costs, as evidenced in this example here. At this particular facility, they were dosing ferric as a method of phosphorus removal. They were also using a belt press to dewater the sludge and were able to achieve about 15% solids on average. The belt press is required to run approximately 8 hours a day for 5 days a week to handle the high volume of solids coming through. After switching their coagulant to ClariPhos to improve phosphorus removal, they quickly noticed that the sludge production decreased quite significantly, and as a result, the belt press was able to be reduced. The operation of the belt press was able to be reduced by about 80%, which means now that the belt press runs only about 1 day a week. In addition, the solids content of their sludge also increased by 40%, from 15% to 21% solids, meaning that there was a lot less sludge overall. And because of this, they spent a lot less money trucking it away to the landfill. When the plant was using ferric, they would send about 75 containers of a much wetter sludge to the landfill per year. But after switching to ClariPhos, they were only sending about 31 containers to the landfill. So overall, this resulted in about $70,000 in annual cost savings, all by a simple switch from ferric to ClariPhos. Regarding the sludge produced by ClariPhos, it is safe to land apply and used as a soil amendment. Rare earth elements have been shown to have very low toxicity and low environmental impact, so that's not too much of a concern. Municipal plants that use ClariPhos repeatedly pass whole effluent toxicity or wet testing at 100% effluent concentration. As well, rare earth metals are not bioavailable to crops, so there's quite minimal potential for stuff like human ingestion. And ClariPhos also doesn't add any foreign metals to the soil, so it is acceptable for land application purposes. The rare earth coagulant also has the interesting characteristic of having a very low freezing temperature of -40 degrees Celsius, which can help reduce that gelling effect that's often seen with coagulants when you use them in cold weather conditions. So for facilities that do have cold winters, this can help eliminate the need for intensive heated storage units or heat tracing of pipes and lines. About 2 winters ago, we started using ClariPhos for an industrial lagoon application at a cheese manufacturing plant. The totes and pumping system were stored in an unheated cube van all winter long, so we really got to see firsthand one of the benefits of this product. No other coagulants really would have been able to endure those cold winter temperatures without a significant negative effect on efficiency. Its non-hazardous rating and minimal corrosivity also make it safer to handle and transport. That really greatly reduces the risk of damage to chemical dosing equipment. So there shouldn't be any compatibility issues integrating this coagulant with existing equipment. So tanks, pumps, and filters that are already existing can, in most cases, remain in use. And ClariPhos can just replace alum or ferric in the process flow. Perhaps with some adjustments maybe to the dose location or the mixing time to optimize the performance. So if equipment upgrades are desired, we can help you design and implement a new chemical dosing system, which can include features such as paste-to-flow dosing or a static mixer to kind of just increase that contact time if there isn't much downstream of the dose point. So before we present some case studies, before Mark gets to that, I did want to talk a bit about pH adjustment as well, just because that's the topic that comes up quite frequently when we speak to clients who want to know if alkalinity dosing is required after ClariPhos addition. Early on, we stated that pH adjustment is typically not required, and that is because ClariPhos is 100 times less acidic than ferric or alum coagulants. And on top of that, you also have a much lower dose requirement. So overall, you need less chemical that's much less acidic to eliminate that phosphorus. So you're really minimizing that impact on alkalinity and pH. Ferric and alum additionally both kind of have limited efficiencies when wastewater pH levels are outside of that typical 6 to 9 range. So ClariPhos is a bit more effective than alum or ferric at pH levels outside of this range. So for example, at high pH levels, alum and ferric tend to speciate. So over a pH of say 8, alum will start to transition to the aluminate ion, which is negatively charged, and it actually repels phosphate. So that really decreases alum's efficiency above pH levels of 8, whereas ClariPhos makes a similar transition only at a much higher pH around 11. So its efficiency at kind of like abnormal pH ranges are a lot better. Yeah, so now that we've covered some of that background information on ClariPhos and how it works, I'll turn it back over to Mark to present some ClariPhos case studies.
All right, great. Thanks, Christine. So yeah, the first case study comes from an industrial wastewater treatment plant in Ontario. It's a large cheese manufacturer that processes about 30 to 40 cubic meters of wastewater per day, and it has an on-site MBR system with a DAF system as pre-treatment. So their wastewater contains many different contaminants: fats, oils, grease, BOD, TSS, as well as phosphorus. So during the first 2 years of operation, the plant, this is before we were involved, the plant used alum initially to try and reduce phosphorus to a target limit of less than 1 milligram per liter. So they initially tried feeding it direct to the main digester tank, but phosphorus removal proved to be inconsistent. It caused several problems, including excess foaming, significant pH swings, which were contributing to biological upsets and the need to frequently reseed the system with activated sludge. So significant consumption of caustic was also needed to balance the pH. So the plant then made the decision to install a tertiary filtration system to feed alum, removing it from the main digester completely. And this helped with some of the previous issues, but required a capital expenditure well into six figures. Maintenance hours for operators also increased since they now had another system to manage with a whole secondary sludge wasting procedure. So in June of 2019, the plant began a trial with ClariPhos, and our recommendation was actually to feed it back in the digester as they originally did with alum, since we were confident they would not experience the same pH swings or biological upsets because it's so much less acidic. And within a few weeks after making the switch, the results were pretty clear. Not only were they getting or using about 1/5 the dosage that they were with alum to achieve the discharge limit, but pH swings were eliminated completely, and even the foaming issues were not reoccurring. So, in summary, they were able to eliminate three major components of their operations. The first being that the tertiary filtration system was no longer needed. Secondly, polymer dosing, which was needed in the tertiary filtration system, along with the alum to flocculate the solids. It was a filter bed type system, so the polymer was needed. So that was now eliminated. And caustic, no caustic addition at all was needed anymore once we started feeding ClariPhos. So pH issues were completely gone. So obviously a huge benefit to the plant. Operators have also noticed that their membranes require less frequent cleaning, and when they do need to be cleaned, there's much less of a hard scale buildup and other deposits, so much less difficult to clean overall. So huge benefit to reducing overall system maintenance. Some other advantages include safer handling for the operators, who at times were manually transferring coagulant to a run tank, and also the ability to leave totes outside in cold weather as needed, since the treatment plant is separate from the main manufacturing building, so totes are being moved back and forth. So it's been well over 2 years now since we introduced ClariPhos, and to this day the MBR has never been running more stable. So the second case study is an on-site biofilter system at a commercial agricultural operation, and the plant's rated for about 20 cubic meters per day and receives sanitary waste from domestic lodgings used by seasonal staff. So smaller system, but we see many of these types of systems around these days. And the plant initially used sodium aluminate actually to try and reduce phosphorus below a target of 0.3 milligrams per liter, but experiencing inconsistent results as well as frequent fouling of the filter media. Achieving targets below 0.5 milligrams per liter does become more challenging with conventional coagulants, and just requires that higher molar ratio, as Christine explained earlier. So at this site, the high dose of the sodium aluminate produced a lot of sludge, which carried over solids into the effluent and the media, and also required more frequent pump outs of the tanks. So in August of 2020, the plant began using ClariPhos, and since then, it's consistently met its phosphorus targets and dramatically reduced sludge production. So they aren't experiencing any carryover and fouling of the biofilter media. So it's funny, the only real issue staff had to deal with after switching to ClariPhos was that the dosage, once we optimized the dosage, I should say, the chemical feed pump was actually oversized to handle the much lower dose of ClariPhos. So, but I mean, that's a problem that can be easily handled by installing a smaller feed pump or actually diluting the product on site if possible. So it's a good little case study that reinforces how important it is to optimize, the performance of these small commercial systems, because in many cases, they're not, the settling tanks may not be designed to handle, increases in sludge production from chemical treatment. So in summary, I mean, overall maintenance is reduced due to less frequent pump outs, less chemical handling, longer life cycle for the media, and just reducing that risk of fouling, and all the while improving phosphorus removal efficiency. Okay, so the third case study is actually from our colleagues in the U.S. for a municipal MBR system in Idaho that's eventually going to have to comply with stringent phosphorus limits of 0.07 milligrams per liter in the warmer season anyway, and 0.35 in the cooler months. So the changes won't come into effect until April 2025. But back in 2017, the plant evaluated several options to meet this upcoming limit. So these included tertiary filtration with aluminum sulfate, tertiary filtration with the rare earth coagulant, or dosing both of those chemicals not together but individually into the directly into the MBR without tertiary filtration. So the team conducted pilot and full-scale testing over a 2-year period, and the chart shows the results and the estimated savings after considering 4 different options. So the first 2 columns show the projected cost for using either alum or rare earth coagulant in a tertiary filtration system, and the next 2 columns are data from alum and rare earth fed directly to the MBR. So you can see highlighted in red there, the pilot trials demonstrated that feeding coagulant directly to the MBR would be more cost effective. And you can see in the bottom row where tertiary treatment costs over 20 years were projected to be between $6.5 and $7 million. So after all the numbers were tabulated, results show that feeding the rare earth coagulant directly to the MBR would be approximately $2 million less even than using alum over that time span. So works out to about $100,000 a year for this particular plant. And in fact, these numbers don't even take into account that the plant also reduced their caustic consumption from 40 gallons per day to about 5 gallons per day after switching to ClariPhos. So obviously contributing to even more cost savings. And I think we have one more here to talk about, and Christine was more involved with this project, so I'll pass it off to her to talk about the next case study.
Thanks, Mark. Okay, so the final case study is an important one for several reasons. So this is a pilot study that is currently being done in Kingsville, Ontario, which is pretty well known for its high concentration of greenhouses in the surrounding area. Wastewater from these greenhouses is sent to the Lakeshore West Water Pollution Control Plant, which has a treatment capacity of about 5,500 cubic meters per day, average daily flow, and discharges directly into Lake Erie. So phosphorus loading has been steadily increasing, and the town is proactively investigating ways to cope, particularly when they have greenhouse dumps in the area. Their phosphorus levels definitely spike up, and the phosphorus load into the plant is pretty significant. So they were looking for ways to kind of mitigate that phosphorus loading into Lake Erie. In March of 2021, Bishop Water, along with the Ontario Clean Water Agency, began a 12-month trial to evaluate the ability of ClariPhos to both improve phosphorus removal and avoid costly capital projects to expand clarifier capacity or add tertiary filtration systems, or simply just mitigate those increasing coagulant costs that would come with the increase in phosphorus loads. The study still does have a few months to go before it wraps up, so we can't share any specific performance data at the moment, but we have seen some benefits so far, and I can highlight some of our observations. So ClariPhos is consistently reducing phosphorus levels in treated effluent to the regulatory limit, even during peak loading periods. We've also seen a dramatic reduction in the amount of floating sludge in the clarifiers, as well as a reduction in foaming in the aeration tanks. Foam reduction wasn't something that has been extensively documented before, so this was a really great benefit to discover this in a pilot test. The better quality effluent was also resulted in higher UVT and better disinfection by the plant's UV system. So that was also kind of a side benefit that we didn't necessarily target for, but it was great to see. Because they were able to achieve such low E. coli numbers in their effluent, that also opened up the possibility for reuse to some surrounding golf courses for irrigation. So again, another side benefit of ClariPhos as well. We also mentioned that it's less acidic than many other coagulants. So after switching at the Lakeshore plant, we saw the pH become a lot more stable and a lot easier to control. And finally, we saw a reduction in sludge as we kind of anticipated. Right now, we're still collecting the full biosolids data on that, but we do know that their runtime of the centrifuge has gone down from about 2 to 3 times per week to about only once or twice a week. So that also saves on operator costs, having someone to man that centrifuge for the time that it's running. The dewaterability has also improved. So we've seen significant increase in percent solids of the biosolids cake by about 5 or 10%, which is another great benefit. So that kind of wraps up what we wanted to talk about in terms of case studies. I will say we do want to continue monitoring this plant. We do plan to compare our ClariPhos results with a baseline ferric period. So we should have those results by March or April of next year. I just want to quickly highlight a little bit about Bishop Water and who we are and what we do. What I'd like to highlight is our technology focus as a company. We've grown a lot over the past 20 years. We've dedicated a great deal of effort to developing our technologies and systems that provide economic and environmental benefits for clients and their communities. We do this by designing systems that are reliable, they're easy to operate and maintain, and have low energy requirements that also require little infrastructure around them. We've got a really great team, and we're proud and dedicated. We're proud of the dedication that our team shows in working collaboratively with our partners to continually improve the solutions that we offer. We do have a number of different solutions that can be used separately or in tandem to address a whole array of wastewater treatment and solids management issues. The Bishop Water solids management solution, which uses the geotube technology, can be used not only for sludge and solids dewatering, but also for shoreline protection, as well as in permanent process facilities that require TSS removal or pre-treatment. On the right here, you can see our biocord reactors, which are aerobic attached growth biological nutrient removal systems. We use them to significantly improve BOD and ammonia reductions, especially when enhancing cold weather treatment is required. They can be easily retrofitted into existing systems or implemented as new installs. In addition to ClariPhos, we also offer a range of products that can help augment treatment or be integrated with our other solutions to allow for turnkey or plug-and-play systems that address more than one challenge at a time. So, for example, our chemical conditioning and polymer injection systems are used in conjunction with our solids management solution to effectively flocculate solids for dewatering. We also supply a wide range of beneficial bacteria that can be used to help with bioaugmentation. So these are blends of different types of wastewater treating bacteria that can be added to a system to help inoculate it or give it a little bit of a boost if you're struggling to maintain that population of a certain type of bacteria, like nitrifying bacteria or bacteria to remove oils and greases. All right, so that wraps things up. Thank you everybody for listening and attending this presentation.
Thanks everybody for your attendance. Enjoy the rest of your day.